sir, and special thanks to Srinivas sir also. As we always say, reading books, attending classes increases knowledge, but attending such activities, volunteering in such activities, which helps in improving the skills, which is very much needed to excel ourselves. So I request all of you to join your hands with IEEE. Let's learn together and grow together. Thank you.
Thank you, ma'am. Now I would like to call upon Vedashri Hedges, a Society IEEE Vice Chair, to speak about IEEE Day 2022 events.
Hello everyone, good morning to one and all present here. A warm welcome to all the dignitaries on the dais and off the dais. I would like to give a brief history of IEEE Day. For the first time, IEEE Day was celebrated on 4th October 1884 by a group of like-minded engineers to leverage the learning skills. Every year we try to celebrate IEEE Day in an innovative manner. Last year, in spite of pandemic, it did not stop us from celebrating IEEE Day. We conducted it through virtual mode. We organized quizzes, etc. This year, we got an opportunity to welcome Dr. D. Venkataramanan sir and Srinivas H.L. sir. Welcome, sir. Welcome. It is our honor that you both are here with us to celebrate IEEE Day. This event is possible because of Shada ma'am, Principal sir, Kurian sir,
Guests to give away the prizes. Second place goes to Balaji Pierce. I request sir to address the gathering.
Good morning, one and all. Chief guest of the day, Dr. Venkataramanan sir, and ISRO Space on Wheels in charge, Srinath sir, and principal of the society. We start a women in engineering society. But women in engineering ಇರಬೇಕಂದ್ರೆ ಅವರಿಗೆ ಕಾಲೇಜಿಂದ ಫೀಸ್ ಕೊಟ್ಟು ಮೆಂಬರ್ಶಿಪ್ ಕಂಟಿನ್ಯೂ ಮಾಡೋದು. ಒಂದು 5-6 ವರ್ಷದಿಂದ ಅದು ಸ್ಟಾಪ್ ಮಾಡಿ. ಸೊ ನಾನು ಮೇಡಮ್ಗೆ ಹೇಳಿದೆ, ಒಂದ್ಸತಿ ಅವರು ಪರವಾಗಿ ಹೇಳಿದ್ರೆ ಮಾಡ್ತಾರೆ ಅಂತ ಅವ್ರು ಕಾನ್ಫಿಡೆನ್ಸ್ ಇತ್ತು. ಅದರಿಂದ ಕೇಳಿದಾಗ ಏನೂ ಹೇಳಿಲ್ಲ. ದಟ್ ವಾಸ್ ಅ ಮೋಟಿವೇಶನ್, ನನಗೂ ಅಷ್ಟೇ ಅವ್ರಿಗೂ ಅಷ್ಟೇ. ಸಿಂಪ್ಲಿ ಇನ್ವೆಸ್ಟೆಡ್ 6,000 rupees and became a member by herself and started Women in Engineering section in SSIT IEEE. It is the first. ಬೇರೆ ಯಾರನ್ನಾಗಿದ್ದರೆ ಸರ್ 6,500 ಕೊಡೋದು, ನಮ್ಗೆ ಬರೋದೇ ಸಂಬಳ ಇತ್ತು, 6,000 ಕೊಟ್ಟು ನನ್ನ ಮೆಂಬರ್ ಯಾಕೆ ಹಾಕಬೇಕು, ಏನೇನೋ ಪ್ರಶ್ನೆ ಕೇಳೋರು. ನಾನು ಪ್ರಶ್ನೆಗೆ ಪ್ರಿಪೇರ್ ಆಗಿದ್ದೇನೆ ಇವಾಗ, ಬಟ್ ಆ ಮೇಡಮ್ ಒಂದು ಪ್ರಶ್ನೆನೂ ಕೇಳಿ. ದಟ್ ಈಸ್ ಅ ಪ್ಲಸ್ ಪಾಯಿಂಟ್ ಆಫ್ ಶಾರದಾ ಗುಪ್ತಾ. ಐ ಫೌಂಡ್ ಇನಿಷಿಯಲಿ ಸ್ಟಾರ್ಟೆಡ್ ದಿಸ್ ಐಡೆಂಟಿಫೈ ಪ್ರೊಸೆಸ್. ಸೊ ಒಂದು ವುಮನ್ ಇನ್ ಇಂಜಿನಿಯರಿಂಗ್ ಸೇರ್ಕೊಳ್ತು. ಬಟ್ ಬರ್ತಾ ಬರ್ತಾ ನಾನು ಬ್ಯುಸಿ ಆಗ್ತಿದೆ. ಬಟ್ ಆಕ್ಟಿವಿಟಿ ನಡೀಬೇಕು, IEEE ಆಕ್ಟಿವಿಟಿ ಕ್ಯಾಂಪಸ್ ಅಲ್ಲಿ ನಡೀತಾ ಇದೆ. ಬಟ್ ಇಟ್ ಇಸ್ ಆಲ್ ಆರ್ಗನೈಸ್ಡ್ ಬೈ ಸ್ಟೂಡೆಂಟ್ಸ್ ಓನ್ಲಿ. ದಟ್ ಇಸ್ ಅ ಪ್ಲಸ್ ಪಾಯಿಂಟ್. ನಾನು ಗೆಸ್ಟು ಹೇಳ್ತಾ ಇದ್ದೆ, ಎಲ್ಲ ಅವರೇ ಮಾಡ್ತಾರೆ, ತಪ್ಪಾದ್ರೂ ಸರಿ ಕರೆಕ್ಟ್ ಆಗಿದ್ರು ಸರಿ ಅವರೇ ಮಾಡೋದ್ರಿಂದ ದೇ ವಿಲ್ ಟೇಕ್ ಇಟ್ ಫಾರ್ವರ್ಡ್ ಇನ್ ಬೆಟರ್. ಸೊ IEEE SSIT ಚಾಪ್ಟರ್ ಈಸ್ ನಾಟ್ ರನ್ ಬೈ ಬ್ರಾಂಚ್ ಕೌನ್ಸಿಲರ್ ಆರ್ ಬ್ರಾಂಚ್ ಮೆಂಟರ್ ಆರ್ ಬೈ ಪ್ರಿನ್ಸಿಪಾಲ್ ಆರ್ ಫ್ಯಾಕಲ್ಟಿ ಅಡ್ವೈಸರ್. ಎಲ್ಲ ಆ ಹುಡುಗರೇ ಮಾಡ್ತಾರೆ. ಏನಂದ್ರೆ ಆ ಹುಡುಗರಿಗೆ ಒಬ್ರು ಲೀಡರ್ ಬೇಕಾದ್ರೆ ಟೀಮು. ಅದಕ್ಕೆ ಶಾರದಾ ಗುಪ್ತಾ 2 years ಇಂದ ಶಿ ವಾಸ್ ಟೇಕ್. ಸೊ ಈ ಸರಿ ಹೌ ಇಟ್ ಸ್ಟಾರ್ಟೆಡ್ ಇಸ್, ಯಾವ್ದಾದ್ರು ದೊಡ್ಡವರು ಫೋರ್ಸ್ ಮಾಡಿ ಹೇಳಿದಾಗ ನೀವು ಬೈಕೊಂಡು ಮಾಡ್ತೀರಾ ಅಂದ್ರೆ ಕಾಲೇಜಿಗೆ ಕೇಳಬೇಕು, ತುಂಬಾ ಹರ್ಡಲ್ಸ್ ಇರ್ತಾರೆ. ಸೊ ನಾನು ಹೇಳಿದೆ ಬಸ್ಸು ಕಾಲೇಜಿಂದ ಮಾಡೋಕ್ಕಾಗಲ್ಲ, ಪ್ರಿನ್ಸಿಪಾಲ್ ಕೇಳಿದ್ರೆ ಇದು 2 ಬಸ್ಸು, ಅದು ಮಕ್ಕಳನ್ನ ಕರ್ಕೊಂಡು ಬರ್ಬೇಕು, ಸಾಯಂಕಾಲ ಕರ್ಕೊಂಡು ಹೋಗಿ, ಇದೆಲ್ಲ ಪ್ರಾಬ್ಲಮ್ ಇರೋದ್ರಿಂದ ನೀವೇ ದುಡ್ಡು ಹಾಕೊಳ್ತಿದ್ದೆ, ಹೋಗೋದಾದ್ರೆ ಹೋಗಿ ಅಂತ ಹೇಳಿದ್ರೆ ಎವ್ರಿಬಡಿ ಅಕ್ಸೆಪ್ಟೆಡ್. ಅಂಡ್ ಒಂದೇ ಒಂದು ಸ್ಟೂಡೆಂಟ್ ಇದ್ರು, ಶಿ ಕಮ್ಯುನಿಕೇಟೆಡ್ ಥ್ರೂ ಇಮೇಲ್ ಅಲ್ಲಿಂದ ರೆಸ್ಪಾನ್ಸ್ ಬಂದ್ಬಿಡ್ತು. ಡೇಟ್ಸ್ ಕೊಟ್ಟಿದ್ವಿ, ಫಸ್ಟು ಆ ಡೇಟ್ ಆಗಿದ್ರೆ ಇನ್ನೊಂದು ಡೇಟ್ ಕೊಟ್ಟರು. ಇವರು ರೆಡಿ ಆದರು, 2 ಬಸ್ ಹೋಯ್ತು ಅಂತ. ಒಂದು ಬಸ್ ಹೇಳಿದ್ರೆ 2 ಬಸ್ಸಲ್ಲಿ ಹೋದ್ರು. ಸೊ ಇಬ್ಬರು ಫ್ಯಾಕಲ್ಟಿ ಹೇಳಿದೆ, ಇನ್ನೊಬ್ರು ಶ್ರೀರಂಗಪ್ಪ ಆ್ಯಂಡ್ ಶಾರದಾ ಇಬ್ಬರು ಹೋಗ್ಲೇಬೇಕು ಅಂತ. ಅವರು ಏನು ಮಾಡಲಿಲ್ಲ. ವಿಷಯ.
So we have requested who are the winners to receive the goodies after the quiz. After the next quiz, we will announce it. Thank you.
These goodies will be given right now.
So, Sanjay, I request Sanjay to please come and receive his prize. Please give him a big round. Next one is Sahana. I request Sahana to please come over. Next one is Aishwarya. Aishwarya, then Mohit. Mohit. The last one is Anudeep. Thank you, Risha and Faisal. Now we will be having technical talk by Dr. Venkataramana sir. Over to you, sir.
Talking about space technology, I don't know how many of you are electronics background, chemistry background, or other domains, I don't know. But I made general this one so that from fundamentals I am covering, little deep I go. So people it takes surface level, some people can understand it, takes an idea. And people who are the domain, they can definitely appreciate as we go further. So once again, I welcome you all for this lecture, and I thank SSIT for giving opportunity to deliver my talk here. So next slide. Next slide. Yeah. So what I will be talking is introduction to communication systems. Basically, satellite consists of 4 subsystems, and it's very difficult to cover all subsystems in just 1 hour. It's just impossible. So instead of talking superficial way of little, then we thought one particular subject we talk in depth, so that you get end-to-end how a data is transmitted from space to ground, and how you design systems, how do you qualify those things, how do you put in space, and how do you get data back. So that was the idea here. So based on that, I made few things here, like transmitting system, receiving system. There are broad diagrams, so many people knowing first thing like that I will cover that, and then the transmission. Then the other transmission system will have other frequency bands. As you all know that we can't transmit data the way we want. Permission is required for those things. Frequencies will be allotted. So before launch of satellite, we take permission for particular frequency, and we say this satellite we are launching at this particular orbit and frequencies. It's international commitment. Our committee is there to create all the frequencies so that the crash will not happen in space. Then the just pull on. Then the exactly the IRS satellite, Indian remote sensing satellite. We have three types of satellites where one is the IRS, Indian remote sensing satellite, where my topic is. But apart from this, there is another satellite called geomission also, geospatial satellites, where we have a lot of transponders where your TV, television, all these things are there, the transponders will be using that, it will be placed in 36,000 kilometers orbit. So that's another set of satellites. Then we have navigational satellites where you get this GPS, all those things. So there's another program. So we have three types of satellites. Now basically now I am concentrating only on IRS right now today's topic. Then the next topic is the leak estimate. Leak estimate means the leak margins, how much power I have to transmit from space and ground, and how much is received in space, whether my system will work or not. Why do I need all those things? I can cover at that point of time. Then the different data transfer shows the photographs. Mainly I am concentrating on photographs here so that you appreciate that the photographs will not available in any textbooks, how we design, how it looks. You will get some idea. There is some idea in a short period I can only give that much glimpse of work only. Then coming to modulations, transmitter modulations, of course there are various types of modulations, we all understand, but briefly I touch upon and take you to the higher level, how we design, then the types of modulations, whatever we have, and the modules specifically used for satellite application. Next slide. Next slide. So the then we need to do filtering because the space is such a place where we cannot afford to radiate whatever beyond the designated orbital band. Because other satellite will be there, our own satellite, maybe foreign satellite, whatever satellite it is, we are not supposed to do interference. So for that we need to have some sort of filtering. So pre and post both types are available. That we look into that. And when we do filtering, what happens? There are some issues now that I filter and I'm happy. No, there are some problems that we look into that. Then the data transmission system from space. Now so far we are talking about the ground to space. Now we are talking space to ground, how the data comes back and how we evaluate it and what are the challenges there. So this is the outline of my talk. Can you go next slide? So fundamentally here we can do the carrier generator means carrier means what? It's the signal what supposed to carry. Now let us say I am talking, is a modulating frequency, is a audio tone. This audio tone if I want to send it in space, it's impossible. Because the frequency is low, I am typically the antennas. It is not possible to put such things and all. So we need to have a high frequency carrier. So high frequency carrier, I put the small signal there on that, let's put modulating signal and put on the carrier. Then it gets go high frequency, translate to high frequency, then you radiate it so that the antenna size will come down. Because the frequency is nothing but the lambda, wavelength, knowing those things. So lambda is E by F. So as F increases, lambda comes down, size will come down. So that we can make a small system. So the drive towards future technology is that how do you miniaturize the satellites in small size? Because every case is a weight. Every weight has a cost. The cost we have to bring it down. That means the rocket cannot lift satellite just like that, no, the way whatever we want we cannot design. So rocket capacity is like let's say PSLV or GSLV it has got its own capacity. Those programs using various techniques. Then we carry data, what are types of modulators, we use that. So once the baseband signal, input signal is given to a bandwidth processor, that is being modulated and modulator, and then you do filter and a power filter. So what are the various modulators are available, what are the various power available, carriers, those things we will see shortly. Now coming back to receiving system, now the signal, whatever comes from space, and we use the free modulator, so the whatever data is there, in the modulated signal, that you are trying to extract the data. That's what they demodulated do that. Then you get baseline output from there. Next. So just to give you small definitions of these things, maybe maybe knowing it, but still I just thought that I got like a short better way. So carrying a high frequency signal or with the information rights signal or that. Modulation we thought that something like any signal will have different phase and frequency. So any one characteristic will vary. So that based on that modulation we define. Then we know that AM, FM, PM, PS, digital modulation, modulation, all of you know very well. So various modulations are available. And because whether you use the solid state or maybe GAN device or HSP using this gallium arsenide or the nitrate, those things, or the TWT parallel wave amplifiers, you can use those things. And then the transmitting antennas also, we have phaser antenna and the shape wave antenna and dual gimbal antenna. There are various antennas you can design and put in space. Next slide. Then the frequencies, what is available in space is that S band, X band, AA band. So these are the frequencies. You cannot use anything beyond this in the remote sensing. So wherever there is a data rate is low, I use S band system. Wherever data rate is medium, let us say AX band. Now today satellites are with AA band. This recent quarter 3, whatever we launched, even if you do not work, your output will not come from the core amplifier. And it's very difficult, even 1 dB, 0.5 dB, 2 dB, we are struggling to get that. That is the last mile connectivity, generally what we say. Like that, in here also, that last 0.1 dB, 0.2 dB, if you don't adjust that, and if you don't get that, it costs a lot for us. We will not get a signal. We started with no use of launching. So we need to have a lot of effort in tuning those systems. So in X band, K band, then why we are going for these many bands, you may have doubts. So there are various data rates, requirements comes. Suppose I put 10 payloads, for example Chandrayana, we have put so many payloads in there. Now every payload data has to come to ground. So we need to collect all the data, process it, then bring it to ground. So how much time we require? Satellite visibility is short duration only. So if the short duration, I will see full data. So that means how is it possible? So I need to go from megabits to gigabits rate. So per second, so much data should come down to ground. So that's how the challenging it is. Now there is a volume of data, then you have compression, we have download full data. Then how to do that? So we need to have compression techniques, all these type of techniques. So based on the mission profile, as I said, which satellite where we put in orbit, based on that, this will be decided. Can you go next slide? So we have to, if you want to go for higher data rates, the higher frequency bands, higher auto modulations, frequency reuse techniques, that means same frequency, auto correlation is low. F1, F2, I put two different polarizations so that it will not interfere. Then store and forward, certain things, information I can put SSR and then when it comes back again, we can download it if possible. Then the data relay system, so one set and the set, we can pass the data and get back. Next slide. So, see, data transmission, this can be adjusted, this or not possible? Okay, fine, leave it, okay. Or you can leave it like this, everybody can see this? No, okay, then we enlarge it, doesn't matter. Let the top wave getting blocked. Okay, doctor, techniques only they will not see because this projector I think very clear. So it doesn't matter. So the expand QPSK transmitter main chain and redundant chain. What we talk about these things, this one. Our life is like this only on phones and all the time. Every minute there will be calls like so issues will be coming even though we come out the station. There will be problems, so we need to address those problems anyway. So this X-band transmitter now, let us say the main redundant system. What I mean is the main redundant system is that most of satellites will have this type of thing because of some whatever care we take in making a system successful, PND test and evaluation thing. But still, there could be unforeseen things happens in space. So in that process, what happens, main system will be transferring the information to redundant system. So that's why the main redundant system should be there. So then SSP is a solid state power amplifier, and then the band pass filter. This is just a broad diagram how the data transmission system will be. Next slide. So source of information, a large amount of data, as we said, we have to get from space to ground, and then how do you do it is baseband data. First we format it, that means the cameras will be taking, suppose a satellite is there and the camera is there, satellite and takes a picture of that. Now how do I transmit to ground? So I need to modulate it to the ground, means I have to format the data, maybe compress low frequencies. At high frequency we generate carrier. There are ways to do carrier generation. For example, I take a low frequency signal, multiply it and get it high frequency. That's one way of doing it. Otherwise, those techniques are old techniques. Now what is the new technique is synthesized version. That means directly the frequency of operation, whatever I wanted. A band means A band frequency, X band frequency. Those are all BC graphs. So we need to have designation ground stations. Wherever I want to download a ground station, we have Pune also ground station. That's it, Lucknow. So there are ground stations are available. You want to download the data. The antenna pattern has to be fixed to that, so that we will receive the data at that location. So for that we may have to steer the antenna or we have to fix the antenna. All those things we decide based on the satellite application. Next slide. So there are several factors influence the propagation of EM that all of you must have studied during your course. So because of this, there will be loss of signal during the transit time. Now how do you overcome those things? So you need to pump more power. If you want more power means ARP have to increase. If you want to increase ARP, antenna size. Power output if you want to increase, let us say I increase. Then DC power also will increase automatically. So the part of DC power is connected to RF power. So I need DC power also wasted. Now once DC started getting heated up, now how do you control? Now thermal systems come into picture. So there are one linked to other. Now high power I want dissipate. If I want dissipate, then good thermal analysis has to be done. Then further, I need good mechanical engineering. How the branches are interlinked to just think over here. Now smooth surface is required because the power of the device has to sit flat on the substrate and the material. So then only deep thinking will happen. So these are the technologies. One is internet further. So it's not that I'm an electronics engineer, I do electronics. It's not so. You need to know little bit. Thermal, you need to know little bit. Mechanical, all these issues are linked. Mechanical, I can't say I want this 0.9 accuracy micrometer. No, it's not possible. Design is not available. Nobody can fabricate for you. Then how do you do it? So it's not that you only design things. You should know that what is the implication. Other side also. Whether a mechanical engineer can produce that particular item. If he can produce that, you have to go back and design mechanical system such a way that he can produce it. Now in that process, you will lose. You are not meeting your goal. You want something, but you are not getting it. Now how do you do it? So you have to compromise here something else. Then is it okay or not? Like this, going forward, backward, around, you have to do some iterations and say it. So design is a challenging factor. Then on top of that, we have our friend noise. Wherever we go, noise is there. So we need to overcome this noise. Then a lot of issues with the noise. We need to solve those things. Now if you don't solve it, what happens? We'll see in future course. Go ahead, things. So this is what we generate and on our own in our own electronic systems. We have to work on this. Apart from these noises also we play a role. So you have to undergo all these things also. Next slide. So this is just originating station and ground station and satellite data. Just I gave you just idea that how you send a signal, how you get back the signal. Next slide. So data transmission now. Let us look this with the satellite transmission happens now. Then we will see the things other things. Go ahead next. So as I already told you, the payload data, payload is nothing but the cameras, when we see the date, space or whatever location, that particular thing picture will be taken and that is converted to pixels, all those things to ones and zeros will be formatted and then transmitted to ground using modulator. So presently now, the S-band data transmission is there at 2 into 480 megabits per second. Can you imagine 480 into 10 to the power of 6 bits per second. Per second, so much data will come. So the satellite is available to you nearly 12 to 15 seconds on ground station. Within that, I need to get maximum data. That's a big challenge in Chandrayaan or Mars mission, any mission. This international community with them, they all want it. The science missions are all with the international commitment. Everybody can come and join in that. There's no problem. So everybody wants to have their data be received at the ground station. So that's another challenging thing. How do you accomplish so many payloads? When you encrypt all the payloads, when data rate increases, then how do you get to 1.5 gigabit per second? Now 377 megahertz was there previously. Now the data rate is 1.5 gigahertz. So the moment the bandwidth is increased, I can call more data. So right now we are getting around 3.2 gigabit data. Now from megabit, now I want to gigabit data. So per second, so much data comes to ground space. Okay, next slide. That is energy to bit ratio, noise to bit ratio, and it depends upon specific characteristics of the filters also matters. So this is the recalculation. What I told, how do you manage these things, power, other things. So let us assume that the transfer frequency 8 to 8.4 gigahertz in our bandwidth. In that they have chosen a QPSK. Then the transfer output, you want any output. Once you decide a transfer output, then you decide the SSP you want, a DW you want, what you want, power amplification based on this. Suppose I want to put data transmission in this event geo system also, there are requirement from some foreign satellite. And you see the component size, how small it is. The filters, how it is designed inside. They are very small in nature. So the moment it's small in nature, you have difficulty in handling also. Next slide. So next slide, yeah. This is what is gone in Chandrayaan 3, Chandrayaan 2. So we need to have systems like this. No, one over there. You make one compartment, then you build over one more compartment, then build one more compartment. Then all these things has to go through the vibration, shock, thermovac, all the test environment everything has to undergo this. So mechanical integrity is very important. So what I am trying to say is that you don't say that you are electronics engineer, you don't bother mechanical. Even they are equally important. Why? Now let us say this packet I take it to vibration lab and vibration lab it fails. Then you have to open the package fully and then check where it has gone on, what has gone on, repair it, and make back. So it is double work for electronic engineers. We don't care mechanical. So mechanical is equally important that way. So you make sure that everything, how do you make it? You see the component size very, very small, everything is microsegments. There is no discrete versions that are here. L, R, L, C, what you see in lab right now, those things we cannot use here at high frequencies. So we need to design those L and C also. Because another challenging thing. Suppose you don't make it top side and output side, and suppose not working, then you need to have matching, so we have stuff there. So you need to match all those things and get the required step frequency. So one is ground, one is power amplifier. Next slide. So test it. Anything goes wrong, how do you replace it? Again put a different device, again retest, requalify. Very challenging thing. Next slide. So coming to modulation, now we have types of modulation. We've seen that BPSK, QPSK, various modulations are there. We look into that. Next slide. So as we have seen that now, if I want to get data from space to ground, we know that the size of antenna, the power is a problem. Then mixing of signals from different satellites, different frequencies, within satellite, outside satellite, other satellites. A lot of issues with frequencies. I think the companies they are very tough time to sort out all these frequencies. Sometimes the frequency is so horrible that it says some comes and sits in center of your frequency of your desired frequency. Taking out is impossible. There is no filter, there is nothing you can do it. You are relieving the problem because you are sitting in the center of your frequency only. How do you challenge? How do you do that? That is a bit challenging now. Then the data, what we see, the general modulation is of analog and digital. So go ahead, go next slide. Next slide, please. So here the analog signal, the multiplexing is possible here. So proper carrier selection we need to do that. Next slide. So simple way is that no simple equation I put just to get a feel of that what data we are doing. S of t is the signal there, then A of t is amplitude, and cos of omega naught is your frequency, omega naught f 2 by f, and f of phi is f. So these are basically the modulation means either will be changing, and with the error is correction is possible. Encryption also is possible because of the our data cannot be seen by somebody else. So we prefer digital modulation because analog modulation again the frequency limitations will come. We cannot transmit more than some frequency. Whereas digital we can go to any level. Go ahead next. So we assume that now it is counted on the ASK, FSK, PSK, and then if you see all those things, the PSK is the best scheme because power and bandwidth we consider the PSK is the best scheme. So generally space systems we always follow PSK only. Next slide. So in this what we are dealing with now, let us say the BPSK, the links are missing of course. Yeah, the first one is the information BPSK, let us say that 0010 is their signal. And then you put frequency comes near or it goes away. That's a single frequency modulation. How do you choose different frequency modulators? One is the BPSK, other is the QPSK, other is the 8PSK. Now, right now, we are using 8PSK in most of the satellites, and this is recent development, 8PSK. Now, you always think that why BPSK not possible or QPSK? Technology has to improve further. So we need to do known modulations. but new modulation comes, new challenges come. Now what is the challenge? When I go for higher modulation schemes, what happens now? If, for example, 8 phases are there, 4 phases are there, previously 2 phases are there. BPSK 2 phases, QPSK 4 phases, 8 phases, 8 phases. Now as we go more and more phases, what happens? The decision regions come down. That means the noise plays a role there, so I lose my beat. Okay. Next slide, next slide. Next slide. So for example, now let us say BPSK, I have 0 and 1. It is just opposite, 180 degree stage difference. Easy to demodulate this, absolutely no problem. Next slide you go. See, now I am going to PSK. You have 0, 0, 0, 1, 1, 0, 1, 1. Now you see the phases are changing like this. 120, 120, 225, 350. Next slide. So any number of PSKs may be used to construct PSK, but 8 PSK is usually highest order PSK model used in this satellite. Beyond this, what happens? More and more, then 16, all those things like go, then decision region is very narrow and errors comes in there, and solving is very tough. Whereas in ground, we can use those things. Higher connotations, QEM, all those things, leadership companies, all those I can use this because I have repeaters here, so that I can increase the I can filtrate, amplify signal against and back. But that is not possible in space, so it's difficult there. So you have 8 states in QPSK. Next slide. QPSK, X, and etc. But be like this. So if you go higher PSK, what happens? Decision regions will keep reducing, we will have noise issues. Go ahead, next. So next slide. So how do you block down QPSK looks now? Let us see that what we see is first one is the 3dB native hybrid. That means there is a carrier there. That carrier I am dividing in 2 parts. Because 2 BPSKs I am combined, 2 BPS models I am combining, I am making a QPSK modulator. So I need a 3dB hybrid divider, then connect to 2 BPS modulators, and again you combine into a power using a power combiner. So you RF carrier is there, and BPSK modulators you get IMQ data. This IMQ data where it comes? It comes from different payloads, different cameras, all those things. I will give data to these 2 modulators. Next slide. So then specifications wise, see 8 to 8.4 I have designed. Now I can't go on changing. There are 3 carriers, let us say 3 frequencies I have in space between 8 to 8.4, and data rate maximum is 105. So 105, 105, 105. 3 carriers that I combine, or 2 carriers, say 105 plus 105. Later when I do it, I get maximum data. But what are the problems here? Now the insertion loss should be 5 dB. That's the big challenging. 5 dB insertion loss modulator weighing is big challenging task. Why? The amplitude imbalance and phase imbalance should be 5 degrees. That means when I put this modulator in temperature, hot and cold temperature, the variation should be within 5 degrees. That's a very big challenging work. You may think what is there in that 5 degrees, but when you work on that, you know that now it is very, very tough job. And how you cannot overrule this because for all your subsystems, whatever we design, there will be a separate quality assurance person. He will be looking at designs and making sure that the designs are perfect. He will not, otherwise he will not clear. So that means third party evaluation is there. So they will check all those things. I'll show you the plots of that. Okay, so next slide. So there are the pin diodes generally we used previously, not certified diodes also using. That is the pin diode whatever we use there. When I say 105, 52 megabits, all those things. Per second, imagine that diode has to switch so many thousands of times. On off, on off, on off, you should do that. So you can imagine that the life of the diode, how it works in space with that many operations. So we need to qualify those things much beyond that. Then only we get the space it works. Next slide. Okay, this we display already explained that how it works. UPS next level. Next level. See, I don't know whether you can see that this first one is 0 degrees. Let us take that as reference. 178 degrees is this. That means instead of 180 degrees bit, now it's sitting at 178. That means 2 degrees only is there. This is a practical thing. I am just showing this. Then if you go down 89.2 degrees, where it's supposed to be 90, it is 89.2 degrees. Then just start up 0.8 degrees there. And here 87.9 is the last plot, right now. That means we start up just 2. That means I have specification of 5 degrees plus minus 5, but I am within plus minus 2 degrees. So designing this is very, very challenging practically. Okay, next slide. So now how do we design? You can see that the hybrid what I told is just down this side, and the red one what you are saying is a power combiner, and top and bottom what you see is the BPS modulator. The whole unit is in 2 inch by 2 inch. Just imagine 2 inch by 2 inch. The whole modulator is done. It's a wonderful job it does that. 52 megabyte, 105 megabyte, 200 megabyte, this model works. For this only government of India has given Independence Award to me, this development only, for this development. Then to try that, the backside, now we need to make it miniatures also. We cannot have two systems, three systems like that. So this system is backside of that. So back to back is connected. You can see that at the top center, the two wires are coming. That wire is coming nothing but from here. So how do you do packaging? This is the way you package it. Back to back, when you put the separate boxes that even takes in this place. Other thing, when you interconnect that high frequency I cannot go. You put a cable, whatever you put, you lose signal. There will be loss of signal. You can't forego those things. So how do you connect it back to back? How do you get those connections? It's a challenging job. Next slide. Next slide, please. Resatellite space is not possible. Chandrayaan, it has to go so many kilometers, 2 lakh kilometers, 4 lakh kilometers, satellite has to go. How to push that to that level? You have to reduce the weight of the satellite, then it is possible to push it. Next slide. This is what the spectrums of PRG spectrum and random signal. How do you test this basically? You are given random data. What do you mean by random data? When you see space, a lot of data comes 10, 10, 10, randomly it comes. We cannot say 10, 10 will come. Anything can be 2 zeros come, 4 zeros come, 5 zeros come, 100 zeros come. We don't know how it comes. Suppose satellite is going on, let us say ocean. Ocean, what difference will be there? It's only full water only. So reflection will be same only, more or less. But if you have that, there is a problem that the demodulator will not work, the bit synchronization will not work. The translations are required there. 1 0 on the translation is there on that will work. Now you have to randomize that, you have to change it. That's what I put processing. The baseband signal has to be processing, that's what we have to do all those things on board. Next slide. So this is APS modulator. What has flown now? The first one is the 45 degree phase shifter, and the center one is the QPS modulator. You can see that there is just 2 inch by 2 inch substrate. 1 inch by 1 inch substrate. You think this 1 inch by 1 inch substrate. That means 25.5 mm by 25 mm. That much is a small size. Now that size, in fact, it should be much lesser than that. This is done because the structure, whatever mechanical structure is available like that. So we have done that for test purpose. Actual case will be much lesser than that. Next slide. So then we come to filtering that post-modulation, pre-modulation. There are 2 types of filterings again. So you are seeing just now the previous slide, PRBS spectrum, that means it is spreading across. So from space we cannot transmit signal such a wide band. So we need to filter it. So what are the techniques there? And how do you extract, how do you compress that particular thing? If you compress, what happens? That also we have to look at. Next. So the all PSK schemes, you know that a lot of side lobes is there, no thing. So filtering is required. That also we understood that. So for that 2 tests are available, post and pre. Unwanted frequency, that's very well known. Once you put filter, it cuts off unwanted frequency. But disadvantage is that it is difficult to design. In the sense, you carry the high frequency, you pay some moderate high frequency, everything is, let's say X band or K band, everything I have at high frequencies. Now designing high frequency filter is difficult to check. Then a separate filter to change the frequency. Okay, disadvantage is now a separate filter for changing carrier frequency. Now carrier frequency moment changes, I need to change this filter also. Every frequency filter has to be changed. And higher cost also, that's always there. Whenever we design the system with complex thing, cost will go. Now what is the other way we are doing this? How do you simplify it? How do you reduce the cost? Next slide we go. For example, now this is what we are saying that filter spectrum, suppose 13 dB is first and second side low. By putting a postmodern filter, you bring it to 20 and 30 dB. You can see that now the direction, these two you can compare the top and bottom PRBS spectrums, pseudo random bit sequence, so PRBS. So that data, how it is filtered now. Why we are doing this? Because beyond this low, whatever you are seeing here, the other frequencies of other satellites will be sitting. So that interference should not happen. Okay, next slide. So to avoid that, now what we do is, to avoid that all this and whatever we are seeing, the complexity, cost, size, weight, all those things, pre-modulated filter will be used. In pre-modulated filter, the data is shaped before giving modulated level. Modulated level will just before giving to modulator, we shape the data and then give to parameters so that the spectrums will be less, size will be less. And since I am doing at modulator level, that is data level basically, the modulator is nothing but the INP data, that is nothing but low frequency only. I am not playing anything with carrier. It's only with moderated data only. So frequency is low. So once frequency is low, absolutely no problem doing so. Next slide. This is how we can design the using LCs, and then we can put that, and you can see the side load has come to 34, 34 dB, 40 dB. You can see the side load what you are seeing. Like whatever we had done previous case, same better than that also we are having here. You can appreciate that now the difference in this. Next slide. So but this is not important. Now when I pass this modulated signal with filter post pre-modulation, when I pass to amplifiers, you see that now spectrum is regenerated again. That is the problem. So whether how much is regenerated matters. Now how do you control this regeneration? Though the amplifier whatever is going input, grey color things you are seeing, that's called parting material. When I put it in satellite or when I put this fellow in a platform of vibration level table, it can undergo a lot of vibrations. So during that vibration these things will not fail. So to take care, and the cables whatever is hanging like this, it will be shaking. Once it shakes it comes out. Or even if it's not coming out, even though it's intact, center of it will get slight disturbance will be there. Once slight disturbance is there, light is gone. We don't know. We can know guarantee. So we need to X-ray of all those things before vibration, after vibration. A lot of work will be involved in this. These are all the challenging things we will be learning in due course. Yeah, next slide. So these are the DWTS, how do you combine, how do you test in dams. Next slide. So the RF power amplifier, the RF output power, efficiency, sidebands, all those things you should keep it, and you have to design that, the DWT output, we spend a lot of money. One DWT costs nearly 5 crores to 10 crores. That is the magnitude of money we spend on the DWT. Now how do we do indigenous those things? There is another thinking we started. So we started doing gallium nitride amplifiers. Gallium nitride amplifier up to some level, 20 watts or something like that. We do it. Now today requirement is 41. Again I am mentioning it, for example. So we cannot use QWTS. We need to use amplifiers with discrete versus discrete. When I want to use discrete, then I need to develop those things. A lot of time is spent on those things. Okay, next slide. So when you use this post-modulation filter, pre-mod filter, so the spectrum, suppose we have 60 dB backup, just now I told you 18 dB to 10 dB. Now we take to 4 dB backup. That means I am attending signal side to be slightly lower. So the side of what I achieved 18 has fallen to 16. Further if I go next slide you go. So it has come to 15 now. So if I give one further lower, the side loads are coming up. The moment side load comes up, it doesn't sit up. So you need to have some balance to move those things. Next slide. So here saturation by doing what happens, side load how almost no changes. So at saturation, yes, I can use any amplifier is okay in saturation, but the lower side is always better. Next slide. Yeah, this is already we are seeing that how side load changes. Next slide. So just to give a feel of port and tray, how much difference will bring the side load first and second load display numbers, how good it is for pre-mod filter level. Next slide. So these are various housings is another challenging thing there. How do you make all electronic circuits in a given package? So that's all we are, these are compartments you are seeing now. Now those compartments, that's another challenging thing there. Though you put cover, some cover, there's a cover on top of that also, on top of that. But the field will radiate from here to there. Inside itself there will be some small openings will be there because it has to, like some cable will connect, something has to connect, signal has to flow. You need some small opening. When you use small opening there, the RF field, there is no link, RF field can go anywhere, RF is everywhere. So it just passes and it interferes other circuits. Then how do you solve it? Box to box, one problem. Within satellite, another problem. Within box, another problem. So everywhere the RF field creates nuisance for you. Because 10 megahertz signal will be there. When you take it to higher frequency, that higher frequency when you upconvert it, it generates some more products. Those products will come into the lower frequency component already existing. So EMC will not pass through. Then you have to have a lot of challenging work there. So RF is a very tough job to solve all these issues. Okay, next slide. So these are the various transmitters and before going to space, how it is packed. You can see there, how we have done those things. Suppose let us say the wires are radiating. So we have copper tape, what you can see there, color, gold color, side, gold color thing. Those copper tapes we put. Now copper tape once we put, the field is restricted to that. It will not radiate, it will not interfere. So there are some techniques as to do because you have done everything, you have delivered the satellite. Satellite level you have problems. How do you solve it? So using this copper tape, then there is a gasket will be there, EMI gasket will be there. You put EMI gasket below the cover so that field will not radiate out. It's like a cooker gasket, imagine. So it will not come out, pressure. Similarly here, EMI field will not come out. Next slide. Now this is all about satellite. Now come back to reception. Now coming to reception side. Let us go next slide. Next slide. So we ground station we always tell EMC or NRSV, RISTRAC, we have various ground stations. What exactly this ground station consists of? Now let's say the antenna, you must have seen registers everywhere. So that dish will comes forward to most of the time will be there, any antenna current will put in the dish itself. So then the losses will come down, like one thing. Second thing, downburst happens there only. By high frequency signal and downward low frequency there, from there it comes to ground station. Your ground station will be somewhere, you have to run it cable, wire, whatever you run it. Losses will come. So low frequency losses will be less. So you bring the frequency lower there itself and run the cable at 20 MHz or 300 MHz, some frequency you can bring it and then can bring your ground station home. After you have demodulators and data processing. So you can see that because this one second. The spectrum what we receive from spacecraft similar looks like that. Down current spectrum will be like that. Then what you are seeing in the center, what has been cut from payload actually. We have processed everything which has become 1 and 0. And this is the thing, and that is coming to picture imagery what we call that is shown here. So based on that, now we decide what should be the ground station. Link method will be taken, G by T we call that. That number will be taken care and made the interaction based on the ground station requirement. So these are the images already we are seeing. Next slide. So this is the first part of our life for any RF communication person. We have to pass this final test. So how you all write your internal exams, all this final exam is very important. So these are our final exam for this. So this is beta rate. So 1 in 10 power minus 6 is the specification. That means if I transmit 10 power 6 bits from space, I can allow only 1 bit error, not more than that. This is a very challenging thing. So one error can come by any means. More than it comes, our quality program will run, quality engineers will not accept the package. We need to do repair. So how do you do these things? How critical it is? Just appreciate that how much problem we have. Go to next slide. So what it consists of now? The data generator is nothing but the data what comes to modulator ones and zeros, those things. And we have shaping filter and modulator, power amplifier. These are all the onboard systems, everything, top line. Now noise and amplification, we add these things because these are the two fellows which is getting added to our signal whether in space or wherever it is, internal outside noise source. Then we amplify the signal also and then due to the oncoming signal. That means the spacecraft signal and noise we generate and combine these things and then down convert it. This is what is happening, bottom line is coming at a ground station what is happening. So down conversion, demodulated, basic signal, flame test, basic test method. This is the way you have to pass through this test separately on the ground. So whatever we do in space, one command has to give it, that has to be demonstrated on the ground first. That test command is executed successfully. Then only I can use in space environment, otherwise not allowed. Next slide. So now what are the challenging things that you should think if these things? So multiple reconfiguration antennas, transmitters, jamming, power sharing receivers in various frequency ranges. It is a challenging task for you people to just giving you. And then the large reconfiguration switching matrix at baseband RF level intersatellite links permitting signals to exchange between satellites according to changing requirements. There's another challenging thing you will have to do it. Right now we are planning it's called SpaceX mission where two satellites will be docked together and go away from the satellites, come together, exchange of information, those things are doing. But this is what is required in the future. Just now we discussed sometime back that the satellite data is available only for some 15 seconds, 30 minutes, 25 minutes, 20 minutes, like that. Then we say the orbit is the orbit. Afterwards, what happens? The satellite is available next to you, only in the next day. But you can't do that. So one more satellite, what is following on, this data has to be transferred to that satellite should take over, and then you should start functioning those things. So these are all challenging things you need to do, things like that. Then the complex and efficient analog, optical, digital signal processing, new modulation techniques, and multiple access techniques. These are all you have to think now. Of course, we started now optical also going on, and quantum communication also we started recently. It takes time. Over some few years, we'll be able to do some things. But right now, the work started in the domain. So if you will, when you join it, probably we will be discussing all those points at that point of time. And system will have sufficiently broadband and may have optical space communication components. Right now, space components are not available in optical domain. You have it ground level, yes, you can use the optical communication, but space there is no components available at today. But we can't stop this. So how do we upscale the component in in-house and use it in space. That is a challenging thing. Yes. Next slide. So that changed my topic. So last is the human space program we have. So we'll be launching human space. Of course, it takes time, another 3-4 years from now, probably. We need to launch before that we do the satellites to make sure that the humans are safe. So we need to put robots or whatever it is in hands and then make sure that there is nothing wrong in that. Things will not go wrong because human is very important. So with this I end my topic. So any questions we can ask. Open for discussion. So no questions, you are not understand anything or you understand everything?
So now you have liquid cryogenic engine.
Take the mic and speak from here.
Sir, it is out of curiosity I'm asking, sir.
Yeah.
We have gone through Nambi Narayanan's the speech in media and rocketry film. Sir, I just wanted to know if this liquid cryogenic engine is being used now or
Yes, yes.
all over.
Yes. They are using it. Yeah. Any question? Just for cryo engine. Cryo engine, what is our cryo? That we are using. Because of the cryo only we could reduce number of stages in rocket.
Payload weight is
Payload weight we can either way we can reduce the weight of the satellite and weight of the vehicle itself. The cryo will take you more time. Compared to vehicle you have this one proportion. I can use this liquid.
What is the scope of satellite technology to 5G?
5G, see, the frequencies are different. Okay. So, this is the as if they the given whatever I spoke just now, 75.5 gigahertz. They are the frequency they are ordered to 5G also. So, that is going on now, probably we may have to shift the higher frequency. So, it's all government decision. Whatever we can do, we have to do it. The question is that components is available. So, if components are available, probably yes, we can do it. Components are available, you have to develop yourself. When you want to develop it, it takes time. And the industry should come forward to do that. Industry has to come and forward, they need profit. They need profit means volume has to increase. Who will do volume? That's the question. Yeah. Any question? Yeah, please.
Hello, sir. So, what is the delay between the transferring of the information from Earth to satellite and receiving information from satellite to Earth? What will be the delay?
It will be milliseconds.
Oh.
It all depends on the orbit. If the actual time, the orbit based on if I am talking to Mars, how much time it takes. If you take in Leo that we are time is different. Leo time is different. Based on height.
Sir, what about the loss, sir? Like, for example, there are so many phones which are supporting the satellite communication and all.
Phones. Yeah.
Like, what is the loss? What is the data redundancy or data loss
So,
rate?
data has to not be there. Microsecond delay is there. If you can see that when you are talking a foreign, small delay will come there. You complete it, but still you are still listening it. So, this much delay, satellite phone, that delay always will be there. Not about terrestrial transmission, what happens now? The other fellow is receiving, is amplifying, again reducing noise, again going next repeater, definitely is happening there. But in space, that is not available. So, you just go through the space, it has no last day, whether we like it or not. So, the power has to be increased. So, power increase also to some extent we can. Beyond that, not possible.
Thank you, sir.
If you are not asking any question, I will ask question. How many of you want to join ISRO? Good. So you understood what is challenging work and you prepare for that. I am not discouraging you. It is very challenging, very thrilling. You love it when you really work on that. That thrill will not get even if you give 1 crore also. So that's how we told some time back also. That the promotions, the increments, salaries, are all secondary. We will not take anything, we will not give any happiness, right? So you have some money in your pocket. That's good enough for you, as long as you get food for that. But happiness you cannot get. Happiness you get only when you do some things outstanding work. So the outstanding work is nothing but this basic work. So that is really gives a lot of happiness. So when some systems, some problems you have solved and when you go home, you are very happy. So you don't go home because problems are there. Having a problem, you will be in office. So our life is like that. Having a problem is that we will be in office only. We will spend time, what our time. Time is not important for us. Problem has to be addressed, problem has to be solved. Now you may ask why people are working like this. So we have schedules like that. Then why do you have schedules like that? Next question. You are only putting schedule, you put schedule relaxed way. It's not that way. Because the satellite and rocket is married together. Right? So the satellite has to be done, prepared parallelly with rocket. Now rocket integration is going on Sriharkota or VSSC they will be doing and bringing to Sriharkota launch. This will be going on. Parallelly will make satellite of the year. So these two will go and launch back. So your date has to be fixed because these two has to develop parallelly. So I cannot say that I will make satellite, then you make rocket. Then rocket people will take their own another 3 months, 6 months. Then we can't launch satellite like that. You have seen 10, 15 satellites in a year. It's just fixed. You need to do that. Of course. Penalty is that you are sacrificing your family. It is always there. You cannot work in both places. So somewhere you are sacrificing the only benefits you relate to country. So finally, whatever you are taken for, there should be some reason for that. So something you are contributing back to the government or department, whatever it is. Do something. Okay, people should remember you have here done this work. Very good, nice. We stayed 100 years, done nothing. What is the use of the state maybe? He is due very short, but wonderful work he has done. That is what it is. So something you will take challenging work in life and do that. Once you decide our mind, you can do it, yes, you can do it. If you say, no, I cannot do it, you cannot do it. You won't get up from seat also, you from chair, you don't think, hey, why should I get up? You can always access to me with my hand. You take it, you don't get up. Then who is the loser? You are the loser. So by getting up something else, you may be seeing the other thing. So similarly, when you design systems also, you look at them all around. You learn many things in that process, which you are not taught. For example, I told one box package, let us say that. Mechanical, how important it is. EMMC point, how it is. Every hole, every dimension, how it is important. Every filter, how it is important. Everything is a challenge. Because we just go back and work. Lambda is equal to C by F, simple frequency, simple mathematical term I am telling. F frequency, you put 27 gigahertz in the bottom, F, and find out what is the lambda. And with that lambda, you put up and have done filter designs probably. So filter designs, you do it. How much size it comes to see. To fabricate that size, how much tolerance you will have. That tolerance you put that the frequency will come and get that the frequency will shift somewhere else. Then you appreciate that how much challenge is there in this. It will not come. Suppose you say that point not 1 mm I want. It will not come point. Fabrication will not allow you to get to that level. Then you need to do back again. Therefore frequency will not match. Then how do you do that? The number of sections increase. All these issues will come. More you increase, losses will increase. How do you do that? Then AR issues will come. So one is linked to other, one is linked to other. So design cycle will become very complex as we go, as we process. As individual element, when you see, it may look simple. But at the system level, yes, it is very tough job. Yeah, any questions? Yeah.
So when satellite goes to the space, is there currently any technology that if something goes wrong, it can self-correct itself? Like something is working on that?
Okay. So just to answer your question, we are done with the MOM mission, Mars mission, what we call. Mars orbital mission, we call it now. Okay, it's like our mother, mom. So, the Mars mission, what happens now? As some time back, he pointed out that, sorry, president may come and how much time it takes. I don't reach how much time it takes. Now, if I send some signal to 4 lakh kilometers and wait for the response, I has to give me the response. That means the acknowledgement will go, SSI received it. Then what I can do next work, what I have to do. Now, going, coming is so much time. I can't wait here. So, on our research call, we have automation that is called. So, we will see that this process, go here, next. Actually, we have done automation. That's how MOM mission is achieved. We have not done many commands. It is doing on its own. So, that automation is done already. Okay. Battery out. Hello, brother, you talk loudly.
Sir, we know that in India we don't have much of the VLSI fabrication. So how does many private companies.
Yeah, see, recently we started indigenous things also. Some companies are available now, private companies are coming up, GATEC is available now, rubber. So now the drive is to make use of our Indian facilities. Question is now what frequency? Next question comes. Before you question, I am only answering that. Okay. So the fact whatever we have in India, there's some limitations are there. So your whole system, let us say that no, you have low frequency, medium frequency, high frequency, all those things. Now, whichever frequency you can use Indian facilities, use those facilities in India. Whichever facility is not available in India, to go abroad and take. So we can take abroad facilities also, and then we can use those facilities. There is absolutely nothing stops us or prevents. Only thing is our self-consciousness, no. When we spend money, we will think. ISRO is very confused in that way. Every rupee what we spend, we look whether really worth or not. If I am coming here, is worth or not, I will think whether something. I think okay, so many students have educated, so many, at least 5% if they say I join ISRO, I am happy. My goal is reached here. So I should tell you people that what is the competition involved in that, what is design challenge. Some of the things that I am not having design work here, I don't have any challenging work in life. ISRO is there for do all those things. Standard people are there, no, I want to only, I don't take any risk anywhere here, I want to have 9 to 5 work only. Simple coding work is enough for me. IT companies are there, yes, okay, no issue. So we can't tell that everybody should be same. Everybody has their own way of thinking all those things. So that way, ISRO will think all those things and we go by L1 quotation only. So we ask some 3-4 companies who are there in that, they will participate in that. Whichever is lowest will take order and try to take items. So there is no bar on that we should import or any such things. Wherever we don't have technology, yes, we are doing. But the challenging thing in the Indian industries has to come out now. Why we are not doing Indian industries? They have their own problems. If you look at their side also, they look volume. Let us say I want design on chip, let us say in India. I have my own factory. Imagine example. Now you give me design. Sir, I want this design to be done in your factory. Okay, fine, you give me. Next is what? Now I design to you. Next you will give me design? No. Because I have to be L1 all the time, that's first thing. How do I become L1 all the time? If somebody scores lesser than me, he will get. So what I do is my manpower, whom I have trained for your work. This is the challenging thing in India. Now then other industry now I have to expand and have more fields in my case. So no, whichever work comes I should be able to do it. Now whether I can do all those things in other countries, you know, like machines and all required, or factories required, or computers required, I don't know what are required for your work. So these are the things. Whereas international ones, they separate whole world. So there is no problem for them. It's not they depend only on India. They depend on so many other countries also. So they will run. Now when we want to do that, now we need quality. Sometime back I told you quality needs to play a big role. So he is the person who is assuring that yes, you are meeting the specifications. Right? So that quality you have to maintain here. As once we maintain quality, even farmers will come. Now why ISRO people are coming to put their payloads in our satellites now? Because the quality is maintained like that. Our Chandrayaan 2 recent also they found out something. People have water found out. Like everybody, we are finding Indians, we are finding out in our own satellites. So people are coming. We are at par with others now. Then now so many countries are coming to launch using launch vehicles. When we launch, we get money for the launch vehicle. So now ISRO is trying to look at how to generate money. So when you people join ISRO, some more things you can think. So what else we can build in India? All will come to India only. So our economy goes up. We will be number 1 in the world. So it's all in your hands. Our time is over now. Your time starts. Yeah, please.
After Apollo 11, why no countries are sending humans to
That is very costly event. No country will come, what okay, we launch, but we put 1% in the orbit. What I gain out of it? Everybody thinks like that, no? Now private people are coming now, they will take you to space tourism now, we started recently. You pay so many crores and you should have crores now first of all to go there. So if you have excess money, you can go around and come back. It's not that somebody will take you free there. That's one part. Second part is a lot of training has to undergo. And money expenditure in money involved is too much. And then very question of name. Where you stand, you are number 4, 5, 6, 7, 8, like that only. So to make that, no, you have to do that. You have to do that. Otherwise, not much will be there. But future, whether human can go and stay in space, that question will be there. So something we can bring from there, or we can stay there, or oxygen there, what is there, we can find out something maybe possible in future, we don't know. We are just exploring more. But that is one cap to India. That's all. One feather we are cutting that. Yeah. Any more?
making us more knowledgeable on data communication and power transmission between space and land, and also making us understand the upcoming challenge. So guys, were you attentive? Then, so guys, you are ready for another quiz, another round of quiz. Sorry, you have to. Here it is. Over to you, Vida.
Just in the form of bits and bytes.
Yeah, it is images. Somebody has already said it. Noise. Please raise your hand.
See, before you answer, you got to raise your hands and then you have to answer. Don't just blab it. Yeah. There's someone.
The unwanted signal which is processed with the data.
Okay, it is correct.
So the next question is, how many types of K-band transmitters are there? I'll repeat. How many types of K-band transmitters are there? See, don't tell it in the group. You got to raise your hand and then tell. 3. Yes, it's correct. See, you have to clap at least, no? Please encourage. Please wait till I complete my question. So I repeat. Why Government of India awarded Independence Award to Dr. Ramana sir? So then you can answer, yes.
QPSK modulator. What are the types of filtration techniques?
Sanjay, please give opportunity to someone else, man. Pre and post. Yeah, it's correct. So the next question and last question is, which is the self-correction system present in the ISRO? I repeat, which is the self-correction system present in ISRO?
Mom.
You have to tell the full form. Just a mom is not enough. You have to go to
Mars are.
Yeah, that's correct.
That's it, guys. Thank you for your wonderful cooperation with us.
So now we are going to announce the winners.
So here you will. Guru Charan.
I request sir to present the goodies.
Madam, will you this time? Madam,
So it's an honor to receive the prize. Guru Charan, please receive the award.
Chetan.
Chetan. So I request Chidanand sir, please come on the dais. Chidanand sir, please come over the dais.
Aisha.
ಬನ್ನಿ ನೀವು ಕೊಡಿ ಸ್ವಲ್ಪ